Okay, good evening again, everyone. Last time we met, we talked about convolutional neural networks, and we were able to delve a lot into some of the really deep principles around convolutional neural networks. And I know it was maybe a bit difficult to grasp everything, right? But I felt it was very important that we understand the intuition behind convolutional neural networks and why it is even preferred over maybe, for example, using a fully connected network for image. In fact, why is it so good with image task? So I'm just going to do a quick recap, and then we'll go on. So of course, we we've we talked about this particular architecture of neural networks being very, very useful, specialized for a particular type of problem. And that type of problem is image detection, or any other kind of grid line data, right? So then we talked about the convolution itself, which is the operation that makes this possible. We talked about why we prefer using convolutional neural networks over a standard fully connected networks for image detection. The fact that a fully connected network would not do a very good job because fully connected networks are very specific, right? If you use it for a two-dimensional kind of use case like images or any other kind of grid, it is essentially going to see each part of the two-dimensional space as a separate place. So if you were to put a cat at the top left, and that you move that same cat to the bottom right, those are two different cats as far as a fully connected network is concerned. But convolutional is better able to detect that, and we talked about some of those things. Also, convolutional neural network has less density, right? Compared to a fully connected network, but it does the same thing. So I went through all of that and then we looked at the advantages. These are some of the concepts we talked about, local connectivity, right? The fact that in a convolutional neural network, you have a small piece, of the network that you are training. You are training a small piece of the network to scan through a larger area, right? So the train part of the network is small, maybe like a 3 by 3 or a 5 by 5, kernel that is kind of how do I put it? Extended into a three-dimensional shape, which we call a filter. We can also call that a filter. And each layer of that three-dimensional shape or each part of it is ends up learning to interpret specific features in the image. So it only connects to that local region. That's what we call a receptive field. The receptive field is just that section of the image that the kernel is scanning at a particular time, right? So that helps to for it to be able to recognize local patterns. Then we talked about parameter sharing. So you are using this same thing to scan the entire image. So you are basically reusing the same parameters. Okay, translation invariance is the fact that if you move something, like I just said, from one part of the image to the other part, because it is only learning local patterns, if it sees that same pattern in another part of the image, it will still recognize it as the same thing. So it doesn't, what it recognizes doesn't depend on the location, in that two-dimensional grid space. So that's translation invariance. Then hierarchical feature learning is now what defines the architecture of a convolutional neural network where you are stacking multiple layers of these convolutions. So each layer does what we call a feature extraction. It learns some specific features and it kind of engineers those features. So like I've always said it, each layer in the neural network kind of does a bit of feature engineering. That's what it does. It does feature engineering, and the features it has come up with gets sent to the next layer, right? So as you're training the network, it's getting better and better at engineering that specific feature or recognizing that specific feature. So early layers begin to learn low-level features, edges and colors, while deeper layers will combine those other features that have been extracted from the earlier layers. They combine them and learn, more complex features, structures, shapes, objects. And the CNN has less overfitting simply because it has less parameters and it generalizes better. So we talked about that. This is basically a repetition of the whole thing, kind of going into more detail. What's a local receptive field? What's a weight sharing? The spatial hierarchy, which I just explained. Um, Translation invariance, which is basically because you have a filter. Just think of it like a small cube, and that is what uh, does that scanning. So we talked about some of these um, key concepts. So I tried to explain a few. Convolution, we've already talked about it. Convolution is actually the operation where you take um, that 3 by 3, you know, square or 5 by 5 square, and you take the numbers in it and you do a multiplication, um, element-wise multiplication of each number in that square with the number that comes in as input. Remember, all the data that comes in, the inputs that come in, the signal that comes in are just numbers. And the weights that you are training are also just numbers. So the same way we were looking at how we're able to a neural network basically works, or a neuron basically works by doing a weighted sum. That's what's happening here. It's a weighted sum, right? Where in this case, you can consider the weights to be what you have in the filters, right? So that's the convolution operation, the weighted sum between the filter and the signal coming in, and it scans across. So it comes up with a sum. So as it is scanning across, you're having an output that is also a combination of the output from each individual convolution. So we talked about that. We talked about filters, feature maps. Stride is basically how many steps, the filter will jump to do the next scan, right? And so on. Padding is the padding you have around the edges. So I'll try to explain this a bit more. But when you go more deeply into CNNs, these parameters begin to matter, right? The stride and the padding. And I'm going to see if I can explain that today. It's always good to explain with some visual aid, but I can make sketches and just to help with that. Then, of course, the activation function. Then we're going to talk about pooling. I did introduce pooling a little bit, and I was trying to explain it. Then stacking convolutional layers. So when you are done with one layer, you can add another layer. Remember, a single layer extracts, some features. Earlier layers will extract, basic features, then later layers. So that's why you have to stack layers. The more layers you stack, the more complex features your entire convolutional neural network is able to do. Then receptive field is that particular area where the filter is looking at. Weight sharing, we talked about that. Spatial hierarchy of features, which is basically, again, how features continue to get more and more complex as the signal passes through the the entire network. Then at the end, we have a flattening, fully connected layers and output. Talk about that shortly. I did try to explain this slide to show you what convolution does. It takes the weighted sum across this. The single kernel will look at this, scan through it, and then for each scan it makes, it's going to put an output, right? And I also mentioned that, yeah, so you have multiple filters. This is one way of looking at it, multiple filters, each contributing. Another way you can view this, which I didn't mention, is you actually have multiple scans. I'll explain that scanning a little bit more. This is a stacking of different layers. So this is one layer, another layer, a third layer, and so on. So what is a convolution? Um, Again, think of this as a filter. It's a 3 by 3 grid, right? The input image is a 5 by 5 grid. It could be much more than this. So what we are doing effectively is that for every scan, right, you calculate the weighted sum of what is in the filter and what comes in from the image. And you sum it and the result is put in here. And then you move to the next one. So effectively, let me start here just to explain again, just to clarify. So the first time you are scanning this section, right? So this same filter here scans, you get a weighted sum between this filter and this area. And that weighted sum goes into this box, okay? Then you move stride. So we now talk about stride. So what is a stride? A stride is the number of steps you take. So if your stride was 1, right, what that means effectively is that after this first scan, you are going to do another scan, okay? And so we take a step of 1, right? That is a stride of 1. So with a stride of 1, I now switch from scanning there to scanning here. So I have taken a single step towards the right. So I'm now scanning here. This same 9 squares, I'm still using this same filter. So it's still going to be the weighted sum of this. And if you look at this, this is 4 times 0, which is 0. 1 times 2 plus 2 times 1, that's 4. Okay. Plus 4 times 1, that's 8. Plus 1 times 1, that's 9. Plus 0 times 0, that's 0. So that's still 9. Plus 1 times 2, that's 11. Plus 0 times 1, that's 11. Plus 1 times 0, that's 11. So we end up with the number 11. And so effectively, we will have 11 in this box. That's what we will have in this box. Let me see if I can move it around a little bit. So this is the result of this second convolution. Then I would move again. I move again a single stride from here to this one. And that is where I will start my next convolution, right? So I start my next convolution here in the third box. Again, it's 9 by 9. And again, we're still using this filter. So we will do the weighted sum, which is 1 times 0, which is 0, plus 2 times 2, that's 4, plus 2 times 1, that's 6, plus 4 times 1, that's 10, plus 0 times 1, that's 10, plus 0 times 4, that's 10, plus 1 times 1, that's 11, plus 0 times 0, that's 11, plus 1 times 1, I don't know what that is. That looks like a 6. So plus 1 times 6, that's 17. So that will give us 17 in this third box. And that effectively is our third convolution. So this is how you do convolution. And yeah, so this would now be in here. So we are now done because we have reached the edge here. We cannot do any more. If we move any further to the right, we will now have up to 3 by 3 section to scan. Okay. So we will now move to the next line. So we will now do still by a stride of 1. So we'll move down to the next here and go back to the beginning. So we'll go back to the beginning, right? And we start scanning again. So this time around, we are now scanning again 3 by 3 here, okay? From this second row first column. And we'll still apply the same weight. So 0 times 1, 0, plus 2 times 1, 2, plus 1 times 1, 3, plus 4 times 1, 7, plus 2 times 1, 9, plus 0 times 1, 9, plus 1 times 1, 10, plus zeros because they're just zeros here. So that gives us 10. So this is what, and we can just continue with that, right? I don't have all the time to do that, but that gives you an idea of how the operation of convolution works. So this will just continue that way, okay, until we are able to scan this. And you notice that by the time we have scanned here, and then we scan this one, right? And then we scan this one, okay? And then we come down here, we scan this one, and we'll also have a value down here. We'll scan this one, right? We'll have another value here. We'll scan this last one, right? That completes the convolution on the entire area with stride of 1. So what does a stride of 2 mean? Now, before we go to stride of 2, one of the things that you will notice here, and perhaps I should go look for a better image, is that if I am scanning, um, the number has reduced. The number of the size of the area has reduced from 5 by 5 to 3 by 3. And like I said, the size of the resulting output area depends not on the size of the filter, nor, well, it actually depends. There's a mathematical formula you can use to get it from calculating it based on the size of the image, the input area, and the size of filter. But it basically is, and also the stride and also the padding. Those are the 4 parameters that you can use to calculate the size of the output. The size of the input, size of the filter, the padding, and the stride. Now, but the size of the output is basically the number of times you are able to shift in the rightward direction and downward direction before you get to the edges. So let's now talk a little bit about some of the things that, when we're talking about convolution, what are the things that matter? Okay, so let's look at this. Okay, so this is kind of showing us this. I could um I'm going to create just an empty canvas. I'm going to create an empty canvas and I'll try to explain all the terminologies so that you understand. So I'm just going to do this, right? I'm going to add a new slide and explain this. I'm going to put this in here and I'm going to use this to explain. So this is an input. It has padding. So when you hear padding, you can see that around here you have padding. And I'm going to talk about that. But the input initially was a 4 by 4, right? Now, normally with the 4 by 4, I could have, if I had a 3 by 3 kernel, the kernel is 3 by 3, the input is 4 by 4. So I could, I can only, without the padding, I can only have, the output will only be 1, 2, right? And that I'll get to the end. And then I'll come down here, right? I'll do another 1, 2, right? And I'll get to the end because I can't go down any further. So the output would be a 2 by 2. So sometimes we add padding. The padding means that I can actually go further out. So the padding allows me to go further out. It allows me to scan a section of the input that is smaller than the kernel. That's what padding does. Because here I would, if without this padding, let's assume that um, I only had this here. I couldn't go outside it because I'll be scanning nans, which is not something you want to do. So the padding is added and the padding is given values of 0. So what that padding does is it allows me to scan, to start scanning, and this is the actual section of the input I'm actually scanning, right? Um, so the actual section of the input I'm scanning is a very small section. This is the section of the input I'm scanning. The other part of it is just, um, you know, it's empty, right? Think of it like when we're using now or something to fill the data, if it is nonce, so it's going to be nonce. But what padding does is that it now allows me to be able to scan more. So because of that, I can start here. I scan, I take a stride of 1, I scan. And that gives, the first one gives me this. The second one gives me this. I take a stride of 1 again. I scan, the third one gives me this. I take the last one, I scan, and the fourth one gives me this. And if I've gotten to the end, so I move to the next line and I start scanning again. So again, I can scan here 1, 2, 3, and 4, right? So that's why I get 4 again in the second row. I come down again, I scan 1, 2, 3, and 4. And I get 1, 2, 3, 4. Again, I scan 1, 2, 3, and 4. And the convolution also gives me this 4 bottom here. So that's what padding does for you. Now, what is a stride? A stride is the number of steps you jump before you go to the next scan. So far we have been doing a stride of 1. So we only jump 1, right? So because we are doing a stride of 1, I'm able to scan 4 times. But I could do a stride of 2. So if I was using a stride of 2, after I've done this scan, the next one I'll have to jump 2 pixels. So when I jump 2 pixels to the right, I am now here, right? And I cannot even jump 2 pixels to the right again, because if I do, I end up going outside of the boundary. So if I were to do a stride of 2, I would only end up with 1, 2 scans. I couldn't do this third one unless I added an extra padding. So again, there are some kind of requirements. Now, if I want to do um, a a span, a stride of 2, I would have to add enough padding to accommodate it, right? So if I were doing a stride of 2, then this would be 1, 2. I couldn't do this one. Then I'll come down and I have to come down 2 steps because stride of 2 is in both horizontal and vertical direction. So this will be the second scan, 1 and 2. And then I couldn't do the third one, just like I couldn't do in the other one because I didn't have enough overlap, right? So if I did a stride of 2, then I am only able to scan, my output will only be a 2 by 2 output. I could do a stride of 3 as well. So a stride of 3 will be 1, and then I move 3 steps, and that gives me 2. And then the next row, I have to go down 3 steps as well and start from the beginning, and then again 3 steps. So if I did a stride of 3, this would be perfect, right? I would not have any um, incomplete or unscanned sections, but I'll also end up with a 2 by 2. So that's what stride means. So I'm trying to explain this so that you understand what those terminologies mean and how they affect the output. So all of these things, padding and stride, will affect the size of the output. It affects the size of the output. In addition to the size of your kernel also affecting. If I were using a smaller kernel, so now I'm using a 2 by 2 kernel, you'll see that with a stride of 1, I can now do 1, 2, 3, 4, 5. So I'm now doing a 5 by 5 output rather than a 4 by 4 output. I'll go down here, 1, 2, 3, 4, 5. That is with a stride of 1. And this same padding of 1 around. 1, 2, 3, 4, 5. So I'm going to get a 5 by 5, right? If I use a 2 by 2 kernel to scan a 4 by 4 input with a 1 um, a 1 pixel padding, right? A padding of 1. Now, I could still use a 2 by 2 and I could use a stride of 2. So if I use a stride of 2, I am going to skip 2 steps. So that'll be 1, 2, and 3, right? And then down, I have to skip 2 again. 1, 2, and 3, like that. 1, 2, and 3. So with a kernel size of 2 by 2 and a padding of 1 and a stride of 2, I will get an output of 3 by 3. Okay, so those are things, those are the relation between those concepts. And there's actually a mathematical relationship, which I would encourage, go do some research and you'll find there's some maths in it. But it's basically something like the size of the input plus the 2 times the size of padding, okay, divided by the size of the stride. Um, I missed something. Divided by the kernel size plus the size of the stride. Okay, so um, that's a formula. Okay, so that's essentially how um, that works. Okay, so let's move on. So we've talked about filters and kernels, and we've seen it in flat view, but in real life, it is actually a three-dimensional tube or three-dimensional prism, like this, where each of these scans for a particular set of features. It still scans through the whole image, right? And then it extracts features and keeps it here. So again, in a filter, since it's three-dimensional, the sum, you can see that this is a weighted sum of the entire filter volume, right? Not just this 3 by 3, these 9 blocks here, but also the 9 blocks next to it and the 9 blocks next to it, and so on, all the way down here. So you're actually having a sum that goes all the way in that way. And that gives us the total weighted sum. So you're actually summing it in this direction. And you can see that this entire filter takes all of the features across multiple features from the input and scanning across the two-dimensional face of the input. And then the output is a single output, which it uses to form the next one. So essentially what is happening here is I take this um, this filter, I apply it to this entire section. Let me draw that. So I take this filter, right? I take this filter here, I apply it to this section, and it's going to give me this single output. I take this same filter, I apply it, I will do a single stride. So basically, well, I didn't draw that very well, but think of it like um, going something like this. Okay. Just think of it moving by one stride. It just moves by one stride. And that piece that it gets moving by one stride, something like this, like this, like this, and then it goes up and then it comes back down. Yes, something like that. This is scanning this small slice moved by a single stride. That will now fall in here into this second box. And so it keeps going like that. So if you calculate it, you see that the number of times you have to move to get to the end will be, because this filter is 3 by 3, you need to move 1, 2, 3, 4, 5 times. And that gives you an output that is 5 by 5 by 1. So this is 5 by 5 by 1. But remember, this is just one filter. So one filter scans this entire thing and gives us a 5 by 5 by 1. So if you have a second filter, the second filter will also come and scan this, right? Will also come and scan this whole thing and give us another 5 by 5 by 1. Okay. And it just keeps going like that. So what will happen is by the time I get like 32 filters scanning each of these, we're now going to have 32 5 by 5 by 1s. And then you stack those 32 5 by 5 by 1s and you get a 5 by 5 by 32, which is basically the output from that entire convolutional layer. And that goes to the next one. So the question you ask is, why does it need this third dimension of so many filters? Remember, each filter extracts a single feature. So the more filters you have, the more features you can extract from each layer. So if you have 32 features, that means, sorry, if you have 32 filters, that means you are extracting 32 features. That's why you have 32 feature maps. Basically, this is a feature map. Just to clarify, this single output that I called a 5 by 5 by 1, that's a single feature map, right? Because you can see it as a two-dimensional um, two-dimensional square that contains whatever features that this particular filter has extracted from this entire thing, right? And remember, this entire thing is the inputs. Think of it as an image that also has multiple features. So think of it like another two-dimensional stack of features, right? This is actually another two-dimensional stack of features coming from a previous preceding layer. That's what it is. So each filter is going to scan this and produce a single feature map. So if you have 32, another 32 filters, the 32 filters will generate another 32 feature maps, which when you stack them together is going to give you another 30, in this case it's 5 by 5, it's going to give you 5 by 5 by 82, prism, which is the output. And basically the output from that is just the same as this and becomes the input for the next layer, which is also going to use its own filters to scan like that. And that is the visualization of how convolution works, right? There are so many visualizations, but rarely do you see the ones that will give you this whole three-dimensional picture of it. But again, like I said, each of these on the Z dimension, the third dimension represents a feature. So if we are to take a single image that is black and white, the black and white image doesn't have depth. So it only has the two-dimensional grid, which represents the actual image. So this will be the image. So let's assume this is image of a cat. I'm going to sketch a cat here. I'm not really good at sketching, but I used to be good at sketching, before, but yeah. So this is the image of a cat, right? So you have this image of a cat in a two-dimensional frame, right? But because it's black and white, it only has only one dimension in this other direction, right? So you are going to have a filter just like what we had before that will a filter just like what we had before that will scan and give you it will scan this and give you multiple feature maps, right? But if the image was a three-dimensional, sorry, if it was a color image, right? I mentioned last time that a color image is made up of 3 or 4 components, depending, the red, green, and blue. So you're going to have a two-dimensional for the red, and you're going to have the same two-dimensional, right, for the green. So this will still show you the cat, the same cat, but this time around, the parts of the cat that are green will really be what you see here, right? Because this is the R, so the parts of the cat that are red will show here. Maybe I should make a better demo. Let's make a better thing. Let me use the green color. So the parts, so you now have a green, right? And so this will be the parts of the card that are green. I might not be every part of the card, just the parts that are green. Okay, then we'll also have a blue. Okay, and that will also be here. So you now have a third dimension, right? So we are basically just stacking the different parts.
Satis, we can't hear you.
Okay, uh, I don't know where I got lost. I think so I was trying to explain that at this point, right, we have each of these feature map is created by a kernel. So you would have um I counted 30 feature maps here. Each of these is a feature map. So you have 30 feature maps here, right? And each feature map is created by a kernel. So you have or a filter. I prefer to use filter, but you see people interchangeably using those two. But there's a slight difference between the two of them anyway. So let's use filters. So filter, so they are going to be 30 filters here. Each filter generates this. And this, so that means the layer that generated this feature map has let's say a 3 by 3 kernel, right? 3 by 3 kernel, and there are 30 of them. 3 by 3. By the way, the depth of the kernel depends on the inputs, the size of the input. So if the size of the input is 4, that is the depth of the input is 4. For example, the RGBA from images, then this kernel will also be 4. But the number of kernels determines, or yeah, the number of kernels determines the number of features you want to extract. So if you want to extract 32 features from this layer, you need to have 32 kernels, 32 um 4 by 4 by whatever kernels. The third dimension of the filter or kernel, the third dimension of the filter is determined by the number of inputs, right? Then the number of filters is determined by the number of outputs you want. The size of the filter in terms of the X and Y is always constant. So you are going to always see filters to be something like 3 by 3 by, you know, N, which is the number of inputs, number of input features. And the number of filters will be the number of output features. So I hope that kind of clarifies it because these are also kind of challenging to understand. All right, so each of these is a feature map, like I have said. This layer has 30 feature maps. This one also has 30 feature maps, and this also has 30 feature maps. That means there are 30 kernels that generated this, and the kernels that these 30 feature maps are going to go into a kernel that is going to be 30 or a filter that's going to be 30 by 3 by 3, right? The reason it has to be 30 by 3 by 3 is because 3 by 3 is the standard size of the convolution, right? While 30 is the number of features that are coming in, number of input features or the number of feature maps. So each kernel is going to generate a single output. So this 30 by 3 by 3 filter is going to generate a single output, right? Um, well, let me not say single output. It's going to generate a single output feature map. It's going to generate a single output feature map. And the dimension of that single output feature map, like I showed you, depends on the size of the input, feature maps, right? The stride, the padding, and the size of the kernel. So, um, that is something to pay attention to. So if we now want another 30 feature maps, we'll have to have 30 kernels. So there will be 30 kernels, right? And then these 30 kernels will now give us 30 feature maps. And then these 30 feature maps are what you are seeing here. There are 30 of them. And because there are 30 feature maps, each kernel to also generate the next set of output has to be 30 by 3 by 3, right? And also gives you the same number of feature maps. It's going to give you one feature map per filter, and then you can have 30 filters if you also want this 30 feature maps. I hope that's not too confusing. Nobody really explained this to me this way, but I hope it is helpful. Okay, then the next thing is what we call pooling, right? Or spatial reduction. So I already mentioned it. Pooling is where you reduce the actual size or dimension of the um of the let's say the two-dimensional plane, right? So let me see if I can really explain this. So you start off with something like this, and you have a lot of them. Okay. Or maybe I should do it differently. Let me use lines instead. So I have this, I have this, I have this, I have this, right? So you basically have a tube, and then okay, so I'm not done yet. So this is a 4 by 4, right? This is a 4 by 4. Pardon the way I'm drawing it, right? And this 4 by 4 has how many um features? So this is how we visualize it. I think in a way it has been ingrained in our mind. There may be other ways to visualize this, right? But this is just a good way to visualize it so that you would have, I'm not going to draw all the lines, right? But the idea is this. This has X, Y, and Z. So let's say this is or H, W, and C. This is also another way that we look at it, H, W, and C. So let's use H, W, and C. So this is H, right? Um, looks really small. Um, yeah, it looks really small, but yeah, so this is H, which is the height of the image, right? And then this is W, which is the width of the image. And then this is C, which is the number of channels. Basically, which the same thing as the number of features or the number of filters from the preceding, um, you know, channel or preceding layer. So I can now take a single kernel. I take a single kernel as a 3 by 3 kernel, right? And I scan each. So of course there are animations for this, right? So for your information, the C, which is the number of channels, has to match the C of the input, right? It has to match. Um, so we now have a kernel that is maybe 3 by 3. Okay. So this is 3 by 3 kernel. So you have a 3 by 3 kernel, but the depth of the kernel always has to be C. In other words, the depth of the kernel has to match the depth of the input. Then this 3 by 3 would scan H and W, and it will give us a single feature map, which is a single plane, just a single plane, right? To give us a single plane. And in this single plane, there is no depth. The depth is 0, right? So I'm not even going to bother drawing it, but maybe I'll just sketch it like this. But it's flat, right? Just think of it as flat. It's basically flat. Okay. Um, but the number of stuff in this, right, again depends on the number of stuff here, right? Plus, well, let me not do plus. I'll show you the exact formula later on. But it's the number of H and W, and the number of 3, and the number of the stride and the padding. But at the end of the day, right, you are going to have something. Let's see if I can bulk select and change the color. Um, okay, I can't do that. But uh, so this will be something else. Let me just call it H prime. So H prime, to show that it is a new H. It may not be the same as H, right? But it's a new height and width. And okay. And the depth is 1. So one kernel gives you this. Another kernel will give you another feature map and so on, right? And when you stack all those feature maps from multiple kernels, that gives you another input that goes to the next layer. This is really all I wanted to explain. Okay, so I think that's okay. The other thing I wanted to now talk about is when we are doing pooling, sometimes we want to reduce this H and W, right? Um, because if you continue to keep the size of this flat surface large, it's computationally expensive. So sometimes we do what we call pooling. Pooling is a process where I can compress all the squares in this grid into a single one. So what pooling would do is um, let's now say I have I'm going to take this off so that I will use a different color. So pardon me. Um, I'm using a different color to show the output. Okay. So we have, so this is the output that comes from this. Okay. And like I said, it's a single feature map. Maybe let's say 4 by 4. Okay, so we have 4 by 4. So this flat 4 by 4 comes from one single kernel. Now, if I have 30 kernels or C kernels, let's say just to maintain the same size, so I'm going to also get another um, output coming here. So this is going to be okay. So it's going to still be not 3 by 3, but H a new height and a new width. It could be the same as the old one. And then even a new C, right? But it could also be the same as the old one. Right. So when we do um pooling, so this is convolution. The convolution operation takes this, passes it through this filter and gives me this. Then I can do pooling. Pooling says I want to make this smaller, right? So what I'll get when I do pooling is basically going to be a smaller grid. Pooling always gives you a smaller grid. Okay, so maybe I can reduce this 4 by 4 grid to a 2 by 2 grid, right? Pooling gives you a smaller grid, but the number of features are always the same. Pooling does not change the number of features, right? In your pooling only changes the number. So how does pooling work? Essentially, what it does is just like a kernel, you actually are going to have a kernel, right? But it doesn't have weights. Pooling does not apply a weighted sum. Rather, what pooling does is that it is going to take the weights and it is going to basically change um it's going to change it. Yeah. So pooling will take this and it's going to change the size. So you also have a kernel that does that. A kernel that does pooling. Let me draw that to show you how that works. What you are doing with pooling is I take a kernel like this, and it's also like this. It also has to have the same oh no, it doesn't have the same depth. I take this and I'm going to look at all this. I'm still going to scan it like I did. So if I have a 2 by 2 kernel for pooling, I'll scan this this four first, right? When I scan this four, I then look at the numbers in these four squares and I do a sum. I do an average or I do a max, right? And then the value that comes from it is what comes in here. So if I do a max, it's called max pooling. If I do an average, that is, I sum the four values in here and I take the average, divided by 4, and I put that value here. That is average pooling. Then global pooling is where you take everything at once. And global pooling always results in a single, an output that has a single, um, it's one by one, basically, you know, on the, um, on the H and W side of it. So that's what pooling does. After doing this, I will move to the next one, right? One stride to the right and the same size as my kernel. And I do that and I'll get the second. So actually, if I am using a 2 by 2 grid, right, to do pooling on this 4 by 4, I should get a 3 by 3. So for me to get a 2 by 2 here, that means I'm using a 3 by 3 um, kernel for the pooling. So effectively a 3 by 3 kernel. Okay, so that is pooling basically, and I just wanted to explain that pooling always makes things go smaller. All right, let's go back here. So like I mentioned, pooling operates on small regions of a feature map. So for each feature map, you do pooling on it and summarizes them into a single value. So that single value, if you are using a 3 by 3 window, a 3 by 3 kernel, to do the pooling, then the 9 values in that 3 by 3 window, you will compress them into a single value or summarize them in a single value. That summarizing is you either use max, if it's max pooling, you select the maximum of those 9 values. If it is average pooling, you select the mean or average of those 9 values. But if it is global pooling, you are going to do the entire thing. You're not going to scan a sliding window across, right? Or a convolution or whatever. Well, it's not really a convolution because it's not a weighted product sum. It's just average. So when you use pooling, you are able to achieve dimensionality reduction by shrinking the spatial dimensions. So you have the width and the height, like I said, and I think I've shown that already. And because you have reduced the dimension, the width and height of the each layer of the signal, as it goes through each layer, the tensor, let me use the word tensor, as it goes through each layer, right? You are reducing the number of parameters for the next layer. Because remember, the number of parameters actually directly corresponds to the dimensions. Um, then pooling makes the model translation invariant because with pooling, it means that things are averaged basically. So it is able to learn more. It is not as noise. Basically, the noise is averaged out. So it's better when it with generalization and prediction. Um, Small shifts, rotations, distortion of features do not affect the model as much as it is learning it. Okay, so these are some of the hyperparameters. I think I've done a lot trying to explain all of this. The kernel size, the 3 by 3 by the depth of the kernel, which depends on the number of input features. The stride, I've explained that, the padding, and then the number of filters. The number of filters determines how many outputs you get, while the depth of a filter determines or is determined by the number of inputs that come in. The kernel size is a dimension of that area that does the convolution, which is a 3 by 3 space. So if you increase the stride, you downsample, right? Um, if you use padding to maintain the spatial size, in other words, the size of the height and the width, most of the time, if you want the height and the width to remain constant across multiple layers, the height and the width of the output that comes from a convolutional layer, if you want to maintain it, as it goes across different layers, you have to use padding to make up. So remember, like when I was showing you how padding, if you use padding, it kind of, if you use padding, let me also show you, um, so let me show you this, right? How all of this come together. So this is a very interesting, um, this is a very interesting animation, which I'm going to show, right? That allows you to see everything I have said. Okay. So what this is showing you is, you see, you have the blue, right? This blue here is the image, right? The blue is the image. Then the broken lines around is the padding that has been added. So you have added padding of 2, right? Around each edge. Okay, you have added padding of 2. Then, because you've added padding of 2, what padding of 2 has done is that, remember, your kernel is 3 by 3. That's this shaded section that is moving. That's always your kernel. So you see that your kernel is also generating the output. The kernel always generates a single output. So you see how by using padding, you are able to generate an output that has a greater width and height than the input. The input was 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. So the input is 5 by 5, but your output is 7 by 7. Simply because we added padding of 2, 2. So that introduces an extra span of 4. And that extra span of 4 is what allows your kernel to scan basically all the way and achieve an output of 7 by 7, right? And this is just a single kernel scanning a single dimension, a single feature map, okay? A single kernel scanning a single feature map. So I could scan multiple feature maps. That would mean this kernel has to be deeper. And then I could have multiple kernels that will give me additional feature maps, which I will stack, okay? So this is really how we should see this. Again, I had shown a bit of, I've shown you a link to animation. Let me just go through this animation again. Um, yeah, so I want to, yeah, okay, this is not what, the link is not working. It's taking us to YouTube rather than the, okay, but I think I could just copy and let's see. I wonder how YouTube hijacked that link. I must have made a mistake. So I was going to show you this. So you can look at this. This is convolution with padding, right? So that this is convolution with padding. Um, Padding is really difficult. The animations really help, right? So I'm just going to go. This is like a regular size. You can see the input here. This is the um height and width, right? And this is the depth, which is the number of features of the input coming in. This is a filter. The filter also has the same yeah, the filter also has exactly the same dimension and the depth is the same. This is the output generated by this filter. So you can see that, and you can see the number of filters, a bunch of filters are coming in. Each filter comes in on their own, right? So the interesting thing that this animation is trying to show you is as the filter gets bigger, the output size gets smaller because the number of steps it can take is less. As the filter gets smaller, right? The output size gets bigger because the number of steps it can take is much more. So that's really what this is. So, but if you want your special dimension, so what we mean by special dimension is the height and width, basically. You want it to remain constant, okay? As long as you have a kernel that is, or a filter that is more than 1 by 1, a 1 by 1 will always give you the same size of output, right? As you could see here, a 1 by 1 will always give you the same size of output. A 1 by 1 will always give you the same size of output. But if it is more than 1 by 1, I wish I could get one of those intermediate states. So this is a 2 by 2, right? And you see that a 2 by 2 will give you less, the output will be a bit smaller and so on. So it's only a 1 by 1, but a 1 by 1 will not do very well in terms of um extracting features because the whole idea of extracting features is being able to look at a larger, feature space, a larger spatial dimension, right? And so for you to be able to do that, right, you have to make this bigger. And if you make the filter bigger, then the output dimension will be less. The spatial dimension of the output will be less. So how do you make up for that if you wanted to maintain the same dimension? That's where you add padding, which we've talked about already. All right. So I still recommend that you go look at all of these animations and try to understand all of these principles. Um, we don't have a lot of time, but maybe we could have gone into that more. So anyway, I'm sure you would have observed anyone that is really paying attention, you would have observed that um, you would have observed that basically the spatial dimension is basically height by width, right? This size, it always gets smaller. But if you want to keep the size the same, you have to put padding around so that the kernel can go further enough to still generate the same number of outputs, the same width and height. Okay, so that's it, right? Basically the typical architecture of a convolutional neural network is for you to have a convolutional layer, and typically you have padding and so on so that you maintain the same spatial dimension. And then you have a pooling layer to reduce it, right? When you reduce the spatial dimension with a pooling layer, you can pass it through another convolutional layer and then pooling layer. So we had these early first convolutional neural networks in the 90s, late 90s, which were designed for recognition of digits, which we are going to do an example of that, shortly. The architecture was just this: a convolutional layer, a pooling layer, another convolutional layer, a pooling layer, then a fully connected layer, right? And that was able to recognize handwriting. And the key contribution of this LeNet, which is how this was called, this particular architecture was called, the key contribution was that it was able to demonstrate to the world that convolutional neural networks can solve image recognition problems, which every other kind of thing struggled. But it had a bunch of limitations. It was shallow, so it couldn't do a lot. It had what we call vanishing gradients. So remember when we're calculating gradients, we talk about exploding gradients and vanishing gradients. When we're doing linear regression and the rest, we saw a lot of exploding gradients, especially if your learning rate was very high. But you tend to see more of vanishing gradients with neural networks, okay? Mainly because of the fact that the way the neural networks are learning because of how the optimizers are, right? They tend to um, compress the weights, right? Remember, we're talking about optimizers and regularization. We're talking about how L1 and L2 regularization tends to make your gradients approach zero, or your weights approach zero. So when your weights approach zero, your gradients approach zero, then you end up having vanishing gradients. What vanishing gradients mean is that the gradient at the end of the gradients you get at the layers that are at the end will be big, but the gradients, because remember you're doing back propagation, so that's one thing I need to mention. This is in the context of back propagation. You're doing back propagation, so up here you have large gradients, right? Um, but back here your gradients will continue to get smaller and smaller until they become very tiny, so close to zero, sometimes almost zero. I know if your gradient is zero, then there's nothing to use to update your weight. So your network will not learn at the early stages because the gradients here will be very small, right? While the gradients here will be large, so networks here will learn. But remember, the early stages are the parts, the layers that are extracting the, early features. If those layers are not learning, right? Because of low or vanishing gradients, then this whole network will not learn. So that's one of the issues when we hear of vanishing gradients. We are talking about back propagation and the fact that the gradients continue to reduce as you're passing it through the whole back propagation chain rule all the way back. So one of the other challenges was it was difficult to scale deep networks simply because of these vanishing gradients. And then as the depth increases, the performance plateaus. Of course, the performance will plateau. Like I said, at a certain depth, the gradients are so low that the layers, in the early stages are not learning a lot anymore. So no matter how many layers you add, it doesn't improve the network. Okay. But those were in the early days, in the late 90s, when this whole CNN became the thing, the big thing, and people started really using it. But there's been a lot more research since then to improve and to counter this vanishing gradients problem. So one of the things that was done is what we call a skip connection. So a skip connection now, you take two convolutional blocks and then you still link the output of one to the input of the output. Um, okay, let's say the skip connection is a connection from the input of a preceding layer to the output of a succeeding layer, right? What that does is it still brings some part of the signal to boost the output from the succeeding layer. So what that does is to help minimize or to boost the signal so that when you are doing back propagation, you still have some measure of the gradient from the output coming in. I'm going to do a sketch of how a residual network looks like. A residual network is essentially two convolutional convolutional layers that are stacked together. It's a network made up of it's made up of a residual network is a network made up of residual layers. A residual layer is a layer that has two conv layers stacked together, and then the input from the preceding layer is it's added to the output of the succeeding layer. I'm going to just show you that shortly. So that's one of the things that came up as an innovation in the early 2000s to counter this whole vanishing gradients problem. And yeah, there were other things that also improved and allowed us to do deeper networks, right? Especially for image recognition. The fact that there was more data, right, from the internet and so on. Remember, internet really came in the 90s, 95, and so on. More data in the 2000s. And then GPUs became more powerful, right? Graphic processing units. So the GPUs now made it possible for us to do all of those calculations much faster, allowing us to basically create much deeper networks. So yes, I talked about this already. Skip connections allows us to solve the vanishing gradient problem. Once you solve the vanishing gradient problem, then you can enable very deep networks. So you now started having networks that were as deep as 50 layers deep, 101 layers, and 152 layers. Think about that and compare that with this Lenet, which only had two layers, basically. It had two layers and a fully connected layer, which is basically for inference. So we are going to try some of these. Okay. Um, yeah, so I think this is kind of a summary. We had other kinds of things. I think I've explained this already. The easier optimization because of the gradients being able to go all the way back, right? Then the network learns residual corrections, identity mapping as fallback. So additional new types of networks, we had the ResNet, like I mentioned, a residual network. We also have the efficient net, which is basically compound scaling depth with resolution and achieves better accuracy with fewer parameters. So yeah, those are different kinds of networks. So let me just do a quick sketch of how a residual network would look like. So let's assume that this is a convolutional network, a convolutional layer rather. So you have two convolutional layers, okay, and then you would link these two convolutional layers, of course. So you have the input that goes into one convolutional layer, and then the output from this conv layer to this other conv layer, and then the output. Then you have a skip connection. So what is a skip connection? It's basically a kind of bypass from the input of this to the output of this, right? An additional signal that is added to it. So what this does is that if the vanishing gradient that you would have, you still have some additional gradient that goes through here. And since this gradient, in the backwards propagation part of phase of the training, since that gradient is not passing through these weights. It is not being affected by the gradients here as well. So it's not, you don't end up with gradients that are so low here. You do have some measure of the gradient coming back here, which will go on to previous layers. So this is what a ResNet is, essentially, a stack of two convnets and a skip connection. So this is what we call a skip connection. This particular connection, that's why it's called a skip connection, because it essentially skips over um it skips over it, right? It skips over the actual um the two convnets and basically links this. So some part of the signal is connected. This was very, very powerful. And as a matter of fact, the first chess playing neural network, was built using this residual network, right? If you have ever heard of AlphaZero, AlphaGo, and so on. So many things were done with residual networks. Anyway, that was before the time of transformers. We'll talk about transformers maybe next week. Okay, so this is a summary of everything before I will jump into a little bit of coding or a lot of coding. This is typically how a convolutional neural network looks like. You have an image, you have a convolution, right? So it's a layer. You don't need to write the code for it. You just use it. Then you have a ReLU, which is the ReLU activation layer. Then you have the pooling, which you can choose what type of pooling, whether it's a max pooling or an average pooling or a global pooling. Global pooling will always give you a spatial dimension of 1 by 1. Okay. Then you just repeat this. This second part is basically saying times 10 to times 1000. Basically, you repeat this pattern 10 times or 1,000 times or 100 times or 12 times or whatever, right? That's just it. And it becomes a deep neural network. So you're always going to have convolution, ReLU, pooling, convolution, ReLU, pooling. Sometimes you may have convolution, ReLU, and then pooling, right? Remember, pooling is to reduce the spatial dimension. So if you don't need to reduce spatial dimension immediately, then you don't need to put in pooling. You can just stack the convolution and ReLU multiple times. And then at the end, when you finish the whole stack of layers, okay, you now add a flattening layer to flatten the entire feature map into a single vector, okay? And then you pass that through it fully connected and you have your output here, which does a prediction, whether you want to predict a single thing and so on. So this is the key takeaway. The CNN use cases, image classification, object detection, um, medical imaging, satellite imagery, video understanding. And then the key takeaway is that the CNN exploits spatial structure. The filters learn hierarchical features. Remember, it's the filters that you are training when you're training a CNN. Okay, the weights are in the filters. And then the modern CNNs will solve depth and efficiency challenges using things like the skip connection, which solve the vanishing gradient, and then efficient net, and so on. And then we'll talk about transfer learning. I don't have a lot of time. I would have liked to really talk about transfer learning, but I'll rather do a bit of hands-on. When we come back next week, we can talk about transfer learning and then other things. So let's jump into this. There are three different image data sets that I want to just quickly show you how to train models on it. And I'm going to start from scratch. So I might yeah, I'm basically going to just build from new. So the first one is a MNIST. So what's MNIST? MNIST is a data set that contains handwriting, basically, right? MNIST is the name of an organization, right? It's an institute. I can't remember the full meaning of that, but it is an institute, right? And yeah, let me put this here. So MNIST allows you to, it's a classic handwritten digit data set, right? With 70,000 grayscale images. So remember I was talking about grayscale, right? So grayscale means it's only, grayscale basically means it's only um, black and white. So you will see that, and the images are 28 by 28. So you have the spatial dimension is 28 by 28 by 1. There isn't any RGB. So you used to learn benchmarking image, basic image classification. Then CIFAR is another data set. This one's the images are 32 by 32 pixels, okay? But they are colored, right? So because they are colored, they are RGB. So you are going to have a three feature channels, okay? CIFAR 10 has 10 classes, while CIFAR 100 has 100. So what we mean by classes is you are classifying the image, it's basically image classification. All of that are image classification. So you are basically going to mention like how many classes. So it's either dogs and cats and things like that. So we're going to look at that. Then ImageNet, this one is a much larger data set, right? It has millions of high resolution images across thousands of categories. So we use this one to train deep neural networks and to power modern transfer learning. So we're going to start with a simple one. Okay, so we're going to start with simple CIFAR. So um let me pull that up. If I already have a notebook for CIFAR, if not, then oh sorry, let's start with MNIST, not CIFAR. Um so remember spend more time on the theory than in the code because my thinking is that um if you understand the concepts, coding becomes easy, right? So MNIST, we can get the data set from anywhere. I think a lot of this you know, a lot of these libraries actually have the data set. For example, sklearn has the data set. Um, I don't know if PyTorch has the data set, so you basically can just pull from the data set. Right. So the MNIST is so simple. We only need a very simple um, convolutional neural network. Right. So we are going to do what we call a simple CNN. So let's do our imports first. Import torch.nn, or let's do from torch import nn. Okay. Then we need a bunch of other things. Optimizers from okay, let me kind of well, you could do this, but I think the standard is import torch.nn as nn. So that also works, right? Then import torch dot optim. So this is optimizers, right? So we need to get optimizers. Then we'll use a bit of torch data loading, right? So we're going to get this from torch utils data or import the data loader. Then we'll import data sets. Okay. This is nice because here we can just get the MNIST data set directly from Torch Vision data sets instead of downloading it from Kaggle or something. But there's another problem which I'm going to get a data set from Kaggle, which we can try out, right? But for now, let's just use the one that is in the Torch Vision module package. Then we'll also import the matplotlib as well, of course, so that we can be plotting all our stuff, right? So these are all the imports. Now, after the imports, the next thing I want to do is to um let's use a GPU if use a GPU if available, right? This is always good. For later on, you'll find that when you want to really train on really challenging stuff, you may want to use a GPU. But for now, I don't use GPUs until I really need to. So for now, you can build your code with a CPU and test it with a CPU. Then when you are sure that it's okay, then you switch to a GPU and run because you do have limited usage on the GPUs. Okay, so the first thing is to pick the device. Device equals touch dot device CUDA. So I choose CUDA if CUDA is available. Again, like I said, CUDA is how you access the NVIDIA GPUs. It's not only NVIDIA that has GPUs, there are a bunch of others, like even the Apple Silicon M1 to M5 series. Then there is the AMD and a bunch of other people who also make GPUs. But the NVIDIA seems to be the most yeah, the most powerful, the most common, and the most popular. So right now, yes, you can see I just printed this to be sure of which device it is a CPU. Right. So now um we'll define a simple CNN, right? We'll use Lenet CNN architecture. We'll start with Lenet first. Okay. For the MNIST, we'll start with Lenet, right? Um, so if we go back to our definition, Lenet's architecture was just convolutional layer pool, convolutional layer F fully connected. So we can just do class. We could also use sequential, right? I think we can also use sequential, but let's use this. We'll initialize during the initialization. Um, Remember to call the parent class and we'll pass the name Lynette and self. This is how you call the parent class to start off. So since it is Lynette, remember Lynette is what? Let me see if I can grab this. Lynette is just this. Let me put this here. Oh, okay. Lunette. It's French, so maybe I'm not even pronouncing it properly. Okay. So this is the most important thing. Right. So I'm just adding this. I don't need all of this other ones. So it's really what I really just need to see is this um architecture. All right. So we have a convolutional. So to get a conv layer from PyTorch, you just use the conv2D. So the conv2D means a two-dimensional convolution. And you can see from here that you have to specify the number of input channels and number of output channels. Remember, the number of input channels determines the depth of your filter, right? The number of output channels determines the number of filters that you have in this layer. While, yeah, the spatial size remains the same. We don't normally worry about the spatial size. That will be auto-detected. So if I'm solving a MNIST problem, I only have a single input channel. Remember, it's black and white. And black and white doesn't have multiple channels, right? Black and white is just a single channel which has a black color. So that's why the input channel is one. Now, the output channels, you can choose anything you like, right? So my smart code thing here decided to choose 6, right? Okay, so let's continue. 1, 6. Then the other thing you will need to specify is a stride. Now, if you don't specify the kernel size, will go by the default kernel size, right? Which is 3. 3, you don't need to specify 3 by 3 because kernels are always square. So you only need to define one dimension, right? So when I say 3, that means a 3 by 3 is kernel. And then padding. So I'm going to say padding is 1. So why do I need a padding of 1 in a 3 by 3 kernel? It is to ensure that I have the same size, coming in, coming out, the same spatial size. This is where that thing, I was talking about. So let me do let me see if I can, like if I have something that the size is, it really is kind of, it's kind of a simple way to think about it, right? Um, a 3 by 3 kernel will always, for it to maintain the same size, needs a padding of 1 at each end. Why? Because this 3 by 3 here, right? By the time you take it and you put it, by the time you take this 3 by 3 and you put it, um, okay, let me draw a single square that represents a 3 by 3. Um, okay, so this is a 3 by 3, right? So let's move this around a bit. Okay, one. Okay, this is the beginning 0, 1, 2, 3, 4. I did 4. And the reason why I only got 4, but this has 1, 2, 3, 4, 5, 6, 7. Okay. Um, 1, 2, 3, 4, 5, 6, 7. But I could only do 4 because 1, 2, 3, 4, 5. So it's actually 5. I lost 2 because of the extra width of this. So what I can now do is add padding of 1 at each end. So if I add padding of 1 at each end, right, what do you think will happen? I add a padding here and I add a padding here. Okay. Remember, this is 3. So the padding of 1 at each end allows me to start one step earlier and end one step later. So it compensates for this extra 2. So that's why I can now start from here and I have 1, 2, 3, 4, 5, 6, 7. So a padding of 1 on a 3 by 3 kernel will always give you an output that is the same size. The spatial area is the same size as the input. So that is why we now have a padding of 1. Okay. So this is very important to note. So with this, I have my first convolutional layer, right? This first one. Now I will do a max pooling layer. Okay. So I can do another convolution layer. Um, Kernel size is still 3 equals 1 again. This will still maintain the same size. Um, we should have a pooling layer, right? Um, I don't know if I should put a pooling layer here, but let's see. I need to get the exact details of the net, how it looks like. But let's assume that I gave myself, yeah, we'll pull it. We'll do a pooling layer and make it smaller. So we'll say self dot pool 1. So we have one pooling layer. So to get a pooling layer, we'll use a max pool, 2-dimensional. So again, max pool 2D. So think about it again. Kernel size is 2, right? And stride is 2. So let me explain this max tool. So what happens is when with a kernel size of 2 and a stride of 2, max pool doesn't have any padding because you are trying to reduce the size anyways. So you're not going to have any padding. So kernel size of 2 and stride of 2. So this is 1. Remember the stride is 2, so this is not counted. This is 2. This is not counted. This is 3. This is not counted. This is 4. So what this does is, since you're having a stride of 2, you're effectively reducing and you're taking 2. So effectively, you're taking this 2. Remember, in max pooling, I take this 2 by 2, which gives me 4, right? The 4 above and the 4 below. And I I am going to I'm going to reduce this 4 into a single thing, right? That's what pooling does. So I'm going to take this 4, um, Okay. I'm going to take this one. So when this 1, 2, 3, 4 squares that is covered by this, which maybe I should make it transparent so that it's easier to see and to think about. So let me make it a bit transparent. Well, it's not even helping. Uh, okay, well, I can't make it transparent. So yeah, so but at least we know that there are 4 squares behind this. So if I take these 4 squares and I combine them into a single square, right? If it's max pooling, I'm going to take the maximum value. If it's average pooling, I'm going to take average value. So this 4 becomes 1 square, right? This 4 becomes 1 square. Um, right. So this 4 becomes 1 square. I s- I move by stride of 2, and the next 4 also becomes 1 square. So I now have 2 squares. Again, 2, the next 4 becomes another 1 square. So I have reduced the 1, 2, 3, 4, 5, 6 squares into 3. Okay. Now let's add, just for the sake of argument, let's add, let's make it an even number, right? It should be an even number. So we'll make it an even number. Right. So there's all of these other ones, which I could have extended it, but oh well, don't have a lot of time. Okay, so right. So back to this. So I now do the next one again, 2 steps. Okay. And I get the fourth one. So effectively, I have reduced this horizontal spatial dimension, the width, from 6 to 2. That's divided by 2. Then, since the stride is 2, I'm going to move 2 here. And again, I do a max pull here, and the max pull is going to give me this one. And then I do another one here, and it's going to give me this one. All right. This one is going to give me the third one, right? And this is going to give me this one. And then again, stride of 2, right? That gives me this one, and so on. So by the time you know it, what I have successfully achieved is that I have reduced the dimension, right? I reduced the dimension of this from 1, 2, 3, 4, 5, 6, from 6, 8 to 3 by 4. So that's what pooling does. So in this case, with a max pool to the of kernel size of 2 and stride, I have essentially reduced the spatial dimension to 2. And then I now do another convolution. Again, the number of inputs should match the number of features. By the way, number of inputs and output in a CNN has nothing to do with the spatial dimension. It's only the pooling that affects that, right? Or padding and so on. Yeah, so in this case, I do the same thing. So I'm still going to get the same size, right? So yeah, I'm still going to get the same size. Here it will be half. I'll still get the same size. Okay. Then I can do another pool, right? Pool 2, which again is a max pool 2-dimensional. Again, same kernel size. So basically we just repeat the same. Stride is 2. Okay. So we'll now then move this straight into a linear layer, which is a fully connected. Fully connected is a linear layer. Now, how do we get these numbers from? So let's think about it. First of all, we are doing, since we are doing MNIST, right? The image is 28 by 28. So that's the first thing, by 1, because there's no depth. The depth is 1 rather, because it's grayscale. It doesn't have color depth. Okay. So when I do this first conv2D, I'm still going to remember because we are using a kernel size of 3 and padding of 1, we are maintaining the size. So the size that comes out here is going to be um is going to still be 28 by 28. Same spatial size, but it's going to have 6 features now instead of 1 because we've come in with 1 input feature and we're going out with 6 output features. Okay, then we do the max pool. When we do the max pool has reduced the dimension, right, by half. We just saw it. So this will now be 14 by 14. Max pool or pooling generally always reduces the dimension of the spatial surface or the feature map. So it goes down to 14 by 14. The number of features is still the same. So it's going to be 14 by 14 by 6. This is what goes in here. Then you now have a conv2. This conv2 is the same as conv1. So it's still going to give us 6 to 16, except that you are now increasing it to 16 features, right? So this will be so we'll now have layer 2. So layer 2 will still have 14 by 14 because we have maintained the size. Kernel size of 3 and padding of 1 will give us the same size. But we now have 16 features, 6 input features, 16 output features. Okay. Then we now do another pooling, right? So when we do the second pooling, still the same thing, right? The second pooling is going to reduce this again. Remember, it reduces by half, so it'll be 7 by 7. By 16, it still keeps the dimension. So we're now ending up with a tensor that is 7 by 7 by 16. So we are creating a linear layer that matches that dimension. That's how we get this 16 by 7 by 7, right? And then the 120 is the number of outputs because you are now saying that there are 120 outputs. The reason is that MNIST gives how many classes are they? How many classes are you going to have for classification? Um, I can't remember, but I need to check. So I need to confirm this. I thought it was 100. Let's see. It's something to check. So you can see that the design of your yeah, it is 0 to 9 actually. So we probably should be having only 0 to 9 classification because it's just that is number data set. But our stuff gave me this. So what this means is that for me to complete it, I have to do a FC2, which will be nn.linear, and it's going to take 120 input and 10 output. The 10 output is to classify the 10 digits from 0 to 9. Okay, and that's it. So that's the architecture. Now the forward is you are basically going to do this. So we will do a ReLU. So remember, after conv1, there should be a ReLU, even though they didn't mention it here. So there should be a ReLU. So you take the input, you pass it through conv1, you do a ReLU, and then you do a pool, a max pool. Um, you do a max pool, which is pool 1. Then you do another ReLU on conv2. Then you do pool 2 again, and then you do FC2, FC1, X. So we do FC1 and do FC2. And we return X. So this is our simple Lenet model. Okay. Simple Lenet CNN model. All right. I hope it is clear how we arrived at this architecture. Okay. Now, the next thing is training the model. Of course, we have to load data first, and then um, well, there's something I forgot here. We're supposed to flatten. After pulling, we should flatten, because if we don't flatten, we'll have problems. So we can do the flattening here. So let me just put that. One way to flatten is reshape. I mentioned that before. In touch, we don't use reshape, we use view. So view is the way of doing reshape. So what this is actually doing effectively is saying, take the first dimension, okay, right? And you know, another way could be, this is if we don't know the dimension, but here we know the dimension is 16 by 7 by 7, right? The dimension is 16 by 7 by 7. So we could just flatten that, right? And use -1. So there are two ways to do this. Let's do it this way. -1, so it's a vector. Then we flatten it to a 16 by 7 by 7. So if we look at this, this is there should be a flatten here, right? If not, we may have issues. We can try it out without a flatten. Right. So that is the model. Now, let's look at training stuff. So we would have um, training loop. So the training loop, we start off with specify the batch size equals 64. This is just kind of showing best practice, right? The batch size is if you are doing batch gradient descent, where you are not going to load all the images at once. Remember, we have 70,000 images here, okay? So if you do the normal full batch gradient descent, you load 70,000 images, and that will slow down your processor and your system will hang. You will not be able to do anything. So instead, we split it into smaller batches, and that's what the stochastic gradient descent is all about. And then you small batches, and then you train on those small batches. Okay, so we choose batch size is 64. Learning rate is this. The number of epochs is 10. These are kind of like standard stuff. Then we do transform. So um transform is something that touch allows you to do, right? Think of it as feature engineering. Okay. Think of it as feature engineering in um in PyTorch, right? In sklearn, we could have used this, but with PyTorch, you basically just use transform. I know we did not touch it in much detail, but yeah, but that's what it does, right? So, um, okay. So transform allows you to transform a series of operations. Let me make this is too tiny. This is too large, rather. Okay. All right. So you create a transform. A transform is basically a series of transforms that you want to create. So this is part of PyTorch's data pre-processing pipeline, right? Just think of it like similar to sklearn pipeline that we're thinking about. The things that you will do as the data is coming in, you follow this transformation. So the first thing is the to tensor. The to tensor is a very interesting transform, right? That is applied to PIL images. So remember that your image is coming in as PIL. So let me put some commentary here, right? The to tensor is going to convert your PIL image to a PyTorch tensor. That's what this first transform does. And it's also going to transpose um the dimensions, of the tensor. So PIL comes in as HWC. So if you remember, when I was doing I was telling you that images, you have H and W, which is a the height and width of the spatial dimension of the image. The spatial, when you hear spatial dimension of an image, that's the part of the image that you are looking at, that you are seeing, right? That two-dimensional space that you are seeing the picture or the image or whatever, right? That's the height and the width. But the C is the depth, right? Where you have the number of channels. So for MNIST, which is a black and white image, the depth is 1, like I have said. But the way and it's always represented, this is the arrangement of the data, HWC, for MNIST. But GPUs and the other libraries, they prefer to process their tensors in channel first order, channel, then height and width. So the transform to tensor will also switch the direction or the orientation, if I may use that terminology, of the tensor so that the channel first by height and width. I'm not going to go into more details on this, but it has some specific meaning. Then the next thing you are going to do is normalize, right? So the normalization that you would do, right? MNIST actually has a mean and standard deviation, which I think we use that. It is good to use the mean. Remember, when you're normalizing, if you don't use the mean, if you don't use a fixed mean and standard deviation, right, it is going to be difficult for you to predict another set of data because the reference points for normalization need to be the same. So that if I even want to denormalize, right, I'll get the same thing. So that's why we kind of use this value is kind of recognized as a mean and standard deviation for the MNIST data set, right? So we use that to basically create that. So this is the normalization. Let me add a bit of commentary as well, just to help with that. Okay. So you can see that this at least tells us that this is the mean and the standard deviation for those. Now let's get the training data. So this is transformation. Yeah, let's see. I need to play this as well. I need to play this. I need to play this. And I need to play this. Okay, so yeah, get the data. So to get the data, we can just pull it straight from um, you know, PyTorch has that. So data sets, yeah, we just get it from this MNIST, right? The root is /data. Train means true, download means true, transform. You now put the transform. So this is the beauty of setting up a transform. What it means is that as the data is getting pulled, the transformations here are applied transparently, they're applied as part of the pipeline. So you don't need to come and do a separate transformation. Again, remember I said transformation is like feature engineering. So you can see it's downloading the data set. As it is downloading, it is applying the transformations here, right, which we had put through this compose. Okay, so we create a data set, then we create a loader for the data set. So with PyTorch, you use loaders, you create what we call um a data loader. A data loader is again a very useful utility tool from PyTorch that makes it easy for you to load data, to shuffle it, and to batch it. So that's why we don't have to worry about all of that anymore, right? You just create a data loader, you pass in the original data set. As you can see, this original data set has the entire 70,000 MNIST images, right? It has the entire 7,000 MNIST, but it's not all 7,000 that you will use, for when you are training. So you need a loader. The loader, you give it a batch size, you tell it how much it should load at a time, and you tell it whether it should shuffle or not, right? So I can add these comments as well. Well, I will add comments later on. All right. So so we have our loader in place. So now that we have our loader, right, there is a test data set as well, which we can also download, right? So let's download our test data set. It's always a good idea to have test data sets because the test data sets they help to check whether your network is learning, whether it's overfitting, underfitting, or whatever. Okay. So you can see that I use the same command or the same function call as I use for this. The only difference is that I have specified here train is true and here train is false. So this function, just this different parameter is enough to tell PyTorch when you're downloading, download the test data set this time around. Don't download the training data set. And yeah, for tests, we are not going to shuffle. So we're also going to create test loader, right? And it's still going to come from, it's still going to be a data loader from the test data set. Batch size, the same batch size that I use, but I choose not to shuffle. It's really not a good idea to shuffle testing data set, mainly because you want to maintain that determine the you want to, I don't know what how to put that, but you want to basically ensure that it's the same thing, right? Determinism, that's what I was looking for. So you want to ensure that when you are plotting your charts and everything is the same. If you are shuffling, you may not get the same um out outputs. So all right. So we run our test data set and we download as well. Now, so we start the model, initialize model. And so to initialize the model, we just learnet, right? Learnet. So create learnet to device. Since remember we had established the device that we were using. We have established it here. So we now move, and remember when we say in PyTorch, you have to move your parameters to a device. If it is a GPU, so your tensors rather, all your tensors are on the device, whether it's a parameter or the signal. Okay, right. So we create the model. Now we create the other training, training um, you know, components. Let me use that word. So we'll start with the criterion. The criterion, of course, is your loss function. Um, so in this case, what would be our criterion? What are we doing? We are doing a um where we're doing classification. So we are going to use an entropy. But which entropy? Are we using a binary entropy or a categorical cross entropy? We're using a binary cross entropy or a categorical cross entropy. We'll use a binary cross entropy if it was two classes, a yes, no, on, off, true, false kind of thing, right? But if we have many different classes, in this case, we are classifying the digits. So it's 0 to 9, right? There are 10 classes. Because of that, we're using a categorical cross entropy. So we will use categorical um, cross. So what they understand here is cross entropy loss. Okay. So that is our criterion. Then we'll also get our optimizer. Our optimizer, we can use a stochastic gradient descent or ADAM, right? Either of them is okay. Adam will converge faster. Stochastic gradient descent, we may have to use a learning rate scheduling because it does not do automatic adjustment of learning rate. Optimizer is in the Optim namespace as we had imported here, right? The touch.optim. So let's use an Adam. Okay. So when you're using Adam, you have to specify the beta, which is the rate at which you are going to change your learning rate. So of course, for optimizer, you have to pass in the parameters of the model as well. We'll pass in this learning rate. So we have our optimizer and we have our criterion. Good. So the next thing now is we move on to the training loop. Okay. So for training loop, you can either put in a function or you can just run it out there. So let me put this in a function, right? So let me just call a function called train. And we can pass in all of those things as well, right? Or we can just fetch it directly from global. So, but let's pass in. So we'll pass in the model we want to train. We pass in the device. We pass in the train loader. So the train loader is going to give us, it's like saying X train, Y train, but instead of passing in the actual values, we pass in the loaders. So train loader, then optimizer, we pass in the optimizer, pass in the criterion, which is a loss function, and the number of epochs, right? Okay. So, um, let's go ahead with the training. So, of course, the first thing is let's PyTorch know that we are in training mode. The reason for that is that it is able to calculate the gradients, it activates gradients and a bunch of other things. So this is model.train. When you say model.train, you're telling PyTorch or the model you are in training mode now. So we can start with initializing training loss to 0, cumulative loss correct to 0. This correct is to measure the number of correct predictions. This is to help us calculate the accuracy. Total is 0, which is the total number of predictions. Okay, so we now do looping through batches, right? Loop through batches. Okay, so to loop through batches, um, batch index, data target. So this should be 4. Okay. So this is typically how you would use PyTorch's loader. Okay, you call enumerate. From this enumerate, the loader has been able, you can get the data and you can get the target, right? The loader has both the X and Y values. Okay. Um, the data set also already knows the X and Y values, so the loader is able to figure it out. And then this is just the index. So the enumeration will always give you this index and then a tuple that contains the data and the target. Okay. So you can check things like maybe, for example, the shape, right? But typically the shape would be batch size, right? So let's say shape of data, which we can find out by just typing data.shape and printing it. The shape of data is normally the batch size. Then 1, which is the number of channels. So remember, it's monochrome, grayscale, and then 28, 28. MNIST is always 28 by 28 size of images. Then target, which is a batch of, so target is the the labels, right, that you are trying to predict, right? So the shape of label will also be batch size, okay? And then um, it should just be batch size generally, right? It should just be batch size. It's a vector. So as usual, when we are doing training, you zero the gradients. Um, So remember, data and target comes to you as tensors, right? As PyTorch tensors. So you can transfer them to the device as well. Remember, we have also transferred the model here into the whichever device we are using, whether it's GPU or CPU, right? So now we also are moving the input data that we are using for training, basically what I call the signal, right? We are moving that into the then let's start zero the gradients. I think we know this already. So we just use optimizer zero grad. Then you do the forward propagation, which is just a model, which is pred. You do the prediction. Um, you can call it prediction or whatever you want to call it, model, and you pass in data. Data is the X value, right? And it's in the right shape. That's the benefit of using a data loader. It loads it in the right shape. So you get that, okay? So this prediction is going to have 10 outputs or 10 values, right? Which is the classification. The data is going to have, again, because you have a batch, right? So the prediction is actually going to be batch times number of outputs. So for each batch, you have 10 outputs. And remember, the number of batches you have is this batch size, which is 64. So we are training on 64 at a time. 64 at a time. Okay. Um, so we now do the loss calculation. So the loss calculation is criterion. You just call criterion on your predicted values, right? And the target. Then you do the backward propagation, right? Which is a backward pass, loss of backward. Then you update the weight. So update the weights, you just do optimizer.step. So remember that that's how you update the weights. Very simple. Okay. Now let's do the other part, which is metrics. Okay. So the first thing is train loss. So we in we need to calculate the total loss. Since we are doing batching, the reason why we have to be tracking the total loss is because we are doing batching, right? So we are training on a batch at a time. So we need to calculate the total loss for a particular epoch. So remember, this train is just training for a single epoch. In that epoch, we are using a batch to loop through. This is slightly different from what we have been doing before. What we've been doing before has been we just we are training on the entire data set at once. So we are not batching, right? So we are running multiple epochs. Now, this single is a single epoch, but we will loop through the epochs. But in each epoch, we are also running through multiple batches. So this is how you train when you have a large data set. You have to batch the data. Okay, so after that, we will now do um, we want to get the highest score, right? Is pred dot max. Okay. So what this does is it gives us the um the predicted class with the highest score, right? And we only need the index. Okay. This is to be able to calculate um you know more metrics. So let's do first to calculate the total, which is a total predicted size. So this is a total. You are going to add the existing total to target or size is basically size zero. Zero is the zeroth dimension, which is a batch dimension. So basically, you're just going to get the total in that batch. So you add it to the total count because we just want to get the total count. So this is basically saying add current batch size to total count because the total count has to be accumulated. Then how many of these are correct, right? To get the correct, you will so first of all, remember predicted is to get the indexes. Let me put this here, right? So that we can understand. So we are trying to get the predicted class. Okay. So let me see if I can explain this. What is happening here is that when you predict, right, it is giving you a distribution. Let's see if I can sketch it. It's giving you a distribution, right? So this is the thing. Think about it this way. You're asking it to predict whether that image is 0 or 1 or 2. What number, right? You're asking it to predict that. Now, um, think about it this way. You have a line, and in this line you have different numbers. So let me just put it. You have 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. Those are the only 9 numbers because it's trying to predict characters, handwriting characters or handwritten characters. Okay, so you have only 9 possible values. I was thinking I could make this wider apart, but oops. Uh, okay, so all right. So now, if I were to plot like a graph of the prediction, this is what happens when you train a model on a regression problem, and it's a multi-class regression, and we're using softmax basically. Oh, I did forget that. This should have been a softmax on the output. Yes, it should have been a softmax. Yeah, it should have been a softmax. So I wonder why I didn't remember that. Okay. But anyway, so let's assume it is making a prediction and the number, let's say the digit is trying to predict is number 9 or number 6. Now, what would likely happen is that for the output that corresponds to 0, it may predict um, a small number. For the output that corresponds to 1, it may predict that the value for 0, it may predict that the value is this, the probability that it is 0, right? This is just probability. This is probability axis, right? So we're just predicting, trying to predict probability that the digit that it is seeing is a 0. And this probability starts from 0 and goes to 1. So it starts from 0 and here is 1. So the one that is really sure of it to predict a high probability. The one that is not sure of it to predict that is a low probability. So typically you see stuff like this, right? Okay. So you can already see that it makes sense to say that the one that has the highest probability is what it is predicting as the number, right? So in this case, it's predicting that 8 is the number because 8 is the one that has the highest probability. That is why you are using max. Basically, we're saying of the 10 classes, give me the one that has the highest value or the highest score. That one that has the highest value or the highest score, that is what I take to be the prediction. Okay. So that's what this basically is doing, in case you're wondering. That's why we are doing this. We are doing this to say, okay, find the class that has the highest score. The class that has the highest score, right, is the one. And that's why we do not take the first value. The first value is the actual value of the prediction, which like in this case maybe 0.9. But this one is which class has that value. And in this case, well, if you go by this example, predictor is going to be 8. which means that class 8 has the highest value. So that is what that's what this means. And that's what max does. This number 1 is to say the axis, right? It has to be on axis 1. Axis 0 is the batch axis. So we're not checking the batch axis, we are checking the axis that actually contains the probability distribution. That might be a bit difficult at this point, but um, I hope it becomes clearer. Okay, so that's why we did this. Then the rest of it is simple. This is to get the total target, which is a total um that we have trained on so far. And then um this is the number that is correct. So how do we know whether it is correct? Remember, predicted is which class did it predict, or did it give the highest prediction that it matches? If it is equal to the target, right? Again, these are vectors. So predictor is a vector of which ones it is predicting. Target is a vector of which one is the actual correct value. The ones that are equal will give you that resulting vector, the resulting vector from this, the ones that are equal will be 1. The ones that are not equal will be 0. So by summing it, all the zeros will, of course, don't add to the sum. It's only the ones that will add to the sum. So it will give you the total number that it correctly predicted. That's what that is. And then we have to use item because everything is a tensor. Everything so far has been a PyTorch tensor. So to pull the actual value out, we use the item. Okay, so that's what this does. And that tells you the total number of correct predictions. And this is a total number of predictions. So we now add that to correct. That will give you so far the total number of correct predictions. And that is how we are getting those parameters, those metrics. That's it. So the next thing is maybe we can just do a print. I should have added loss. I should have added loss. Um, yeah, I think I want to add loss. So let's see, losses equals losses dot append loss item. So again, loss is a yeah, this loss is just going to keep jumping around. So let's losses um yeah. So this is all training. So the losses and then we can print the progress every 100 batches. So remember, we're taking 64, there are 70,000, so there'll probably be about 1,000 something batches. So if batch index modulo 100 is 0, then we can print a whole bunch of stuff. Epoch, this is the epoch we are in, and I'm just going to bring this in so that um all right. So you print the epoch and then the batch index times length of data divided by length of train loader or data set. So this is kind of how much you have trained compared with the total size of data in the data set, right? And then this is 100 times the batch index divided by train loader, right? So then the loss. So this is yeah, this is a loss, actual loss. I was still also tracking the loss in the list of losses. So that's it. And we can now calculate stuff like, for example, um, we can calculate the average metric. So we can calculate the average loss, which will be the total loss, which I've calculated divided by the total number of items, right? The length of the train loader is 70,000 in this case. Then we calculate the accuracy, which is just 100 times the number that we got correct divided by total, which is more or less what this is calculating, right? And then we can return average loss, accuracy, and losses. Yeah, so that is our training loop, or this is just single um epoch in our training loop. It's a single epoch. We are just running through the batches for a single epoch. So if when we want to train, we are actually going to run that training loop multiple times. Let's now run a testing tests function. So the test function, again, will pass in the model device. Then we'll have the test, this time around the test data, then the criterion. For testing, we only need the criterion. We don't need the optimizer because we're not training. Okay, so we evaluate. So it's just evaluating the model. So we switch the model into eval mode. So in the evaluation mode, we just model.eval. So we initialize the values, total equals 0. And then we can also keep the losses. We can also keep track of the test losses. This is in case we want to plot like a graph of with touch no grad. If you want to plot a graph of whether it's overfitting and all that kind of stuff, bias versus variance. So it's good to have both training and test losses. Okay, so yeah, so this is we need whenever you are in evaluation, it's always good to put everything in this scope, this touch.no grad. Basically means don't try to save any gradients because I'm not training this model. I'm just evaluating it now. I'm testing it. So you don't need to save gradients when you are running a forward pass. Okay. So that's what this does. Then, so you do a loop again using a test loader. So just like in the training, you have to loop through the batches. You cannot just load all the data at once. Okay. So again, we move the data to the device. And then we do the forward propagation. And that is simply the same thing. Spread equals model data, right? Then we calculate the loss, still using the same criterion. And then we calculate the accuracy. It's still the same approach that I just explained to get the prediction of which one has a max value. And then we add the total, same thing as we did, basically the same thing. We calculate the total predictions, and then of those total predictions, which ones are correct is comes from which ones are equal to target. We do a sum and we extract the scalar value from the tensor. Okay, and that's all. So after we have done this, we can step out completely of this and just calculate average metrics. So you have average loss. It's going to be the total test loss divided by the number of items in the test loader. Okay. And then the accuracy is still going to be 100 times the number that is correct divided by the total. And then we return average accuracy and losses. We can also do a print if we want and print all of that. Test sets, average loss, average loss to 4 decimal places. Okay. And then correct divided by total, and then accuracy to two decimal places. And then you add a percent. All right. All right. I think I misplaced the parentheses. So we now have our test function that runs batches. So this is now the main training loop where we can now, you know, train losses, train accuracies. Okay, well, I guess, um, yeah, it's using averages. Okay, we could use the averages rather than this. But I think I like not having to use the averages. Okay, so to train this, train loss, train accuracy. This is the epoch train losses, which is giving you this one will really show you how the thing is actually, zigzagging down the loss landscape. So I like to see that. Yeah. So let me add that train losses epoch. Anyway, I'll come to that. So the train losses, the accumulated train losses, and the accumulated test losses. Criterion for tests and right. And this is the main training loop. So we're basically just doing training, testing, training and testing, training and testing. Okay. So training loop done. So you can see we start with a high loss and then the losses are going down. Of course, once you start seeing your losses going down, it means your model is learning. Now it goes back up again because this is a new batch. So in the new batch, it needs to learn on the new batch. So again, you start seeing the losses go down and then loss go up again the new batch. So this is why it's good to keep tracking. So see, that's the thing with batch training. Batch training, you do have a situation where, okay, so all of this is epoch one. Now we are in the second epoch, right? In the second epoch, we are going to train again on multiple batches until we get the 60,000. So we had 70,000, 60,000 are for training and 10,000 are for test. So you keep seeing the loss goes up and down. It goes down, then it comes up. But in the second epoch, you see that the loss doesn't really go up. It's kind of around the same area. Now it goes down, and even when new batches come in, it still stays down. So it is learning. Okay. So now while this is training, I'm going to add a bunch of visualization. So I'm not going to spend time on this. Let's just put this here. So for visualization, we're going to create subplots and we're going to plot the metrics, train losses, test losses over time. Okay. Then epoch 4, we did 10 epochs. So this is a really bad, uh, maybe overfitting or something, or maybe a batch that we never touched, right? But it's getting better and better. Now, the interesting thing is you can save the model. So this is how you can save the model. You use store just save, right? And you save it to a file. You can download this file and keep it somewhere. And when you want to resume training, you can come back and resume from here. So you can keep training your model. Right. So the loss is also getting better, even though it's still fluctuating. Okay, so we're on epoch 7. So one of the interesting things that you want to do when you are training models like this, especially for visual image recognition, you want to be able to print the image, right? So that you know you can actually see the image how it looks like, and then see whether the prediction is correct or not. So um, I'm going to share a script that does that. So I have this really, really big. So let me just stick this in here. This is for visualization. It's a really long script, and I don't have time to explain it. But um, oh, okay. So training is complete. You have an accuracy of 9858 over 1000 in the test set, which is 98.58. That is really good. Um, you have, yeah, and you could see that it kept increasing. Initially, um, Originally, it already started with a very high accuracy. So they were day in those days, it was you couldn't get this kind of accuracy with stuff like this. Let's plot the yeah. So this is a plot of um loss, right? I don't know why the test loss is 0, but yeah, the training loss keeps going down. This test loss probably has issues. Let's see. Um, so I have probably missed something. Yeah, but anyway, you see that you also have a pretty high accuracy, test accuracy, even though it keeps fluctuating, right? And the train accuracy starts from this low and then goes up. So we can save the trained model. And then after saving the trained model, let's see if we can visualize. Um, let's see if we can visualize. Let's see if we can visualize. So I'm using Lynette. Um, well, this is kind of visualize dataset samples. All right. So this is kind of visualization of it. Um, the script is pretty long, but it's essentially taking the image data and printing it as a grid. So there's a whole bunch of this. There are actually helper functions to do this as well. So you can see this is the data set. This is a random, there are 70,000 um, you know, data points, right? Basically containing this information, pixel information that you print this way. And this is the data set before trying prediction. This is just with labels. And you can see the labels are okay and are correct, right? Then this is based on the model we just trained, what it predicts. So the actual, like in this one, the actual label is 7 and it predicted 7. Confidence 100%. And when you see confidence 100%, that means that is the value of the output, right? We can actually go in, unfortunately, we don't have more time, right? But we can actually go in and like check out the output from each of those fully connected layers. But a confident 100% means it did not even think that it was any other thing, right? So these are all greens. Green is color that is used to indicate that it did a correct prediction. There are a few wrong predictions like this one. Yeah, so the true value is 3, and you can see it really looks like an 8. And the prediction is 8, but the confidence of that prediction is very low. So we can already see that the model, maybe if it was trained with more data, it could predict this one correctly. Um, so these are the models predictions mixed. And then you have some of these incorrect predictions. So this one, the true value is 6, but it predicted a 1 with confidence of 99.8. So predicting a wrong value with high confidence. It predicted 5 instead of 8 with this confidence. Here it predicted 6 with a confidence of 99.7. The actual value is 5. So Well, it's not really doing very bad. 98 point something is a pretty high percentage. Um, Even humans can make mistakes in these situations. Here it predicts 5 instead of 3. Here it predicts 9 instead of 4. I would have actually expected it to get a 4 here. Here we don't even know what this is, but they say it's a 6 and it predicts a 0 and so on. So yeah. So that's MNIST and it has taken all the time. But I'm going to share this notebook and you can actually just use this same approach. Just swap out your model, um, use a different data loader, and you can do the ImageNet, and you can also do the Cipher 10 or Cipher 100. So this is how you train models. This is basic image recognition. Later on, you can now build deeper neural networks and so on to do more advanced stuff. So that's it from me. This was a very long one, but I hope we all enjoyed it. Thank you.